can start today. As I promised yesterday, today we're going to start a lecture talking about timber arches, tapered, carved, and beach covered beams, which means basically in Italian would be archi, travi curve. Tapered means, we said yesterday, beams with variable sections, with the travi rastremate. And then beach covered beams are travi centinate in Italian. So we're going to see, since none of those beams complies with the dell'Aquila theory, we're going to see how can we extend the formula that we learned in structural mechanics also for the use in these cases here. So we will start by giving some advice about structural forms, basically, something probably you already know. Then we talk about some basics of arches, carved beams, the shapes when it comes to arches, some criteria for preliminary design, then some structural concepts, very little, not much information about snow and wind loads, because you had a specific lecture talking about wind, as you saw with the new regulation, calculating the wind loads is becoming more complex than in the past. Then we're going to talk about carved members, and we're going to see that due to the curvature of the lamination, we will have to take into account what we call in English eigenstresses, which means autotensione in Italian, just to use a word that probably are more confident with. Then we will see that when we bend or when we have some carved members subjected to bending moment, there will be a different distribution of stresses parallel to the grain. So we won't have anymore the linear distribution of stresses, but the linear distribution of stresses will become a non-linear distribution of stresses due to the curvature. And then also we will have some stresses perpendicular to the grain that we will have to some way estimate. Then we are going to talk about taper and beach covered beams. So those different kind of beams done in this way, for example, or this way, or in this way. We're going to give some advice, some general concepts about first and second order analysis. Usually what we do in 99% of the cases is linear analysis. However, the Eurocode suggests also the possibility to do a second order analysis. So I'll give you just some basic concept about how to do the second order analysis. Ultimately, mistake verification, including out-of-plane buckling. Already yesterday we started saying something for the focal frame, not to take into account the in-plane buckling and the out-of-plane lateral torsional buckling. Then something about serviceability mistake verifications. So we start, as I said at the very beginning, by saying a few words about the structural forms, some concepts that probably you have already learned in statics. So if you want, the problem would be how to cover a certain span. So you have to cover a span, let's say, of 20 or 30 meters. What kind of structural form can we use to cover this span? We have, of course, different possibilities. The first possibility is using a beam, or a systems made of beams. In a beam, you know very well that the resistance to vertical load is mostly achieved by bending. Bending and shear, of course. So, a beam, it's a suitable solution if you use a material that can effectively resist to bend and to shear. Now, what is a material that can suitably resist to bend? Usually, I would say it's a material with a symmetric behavior in tension, in compression. Because bending, as you know very well from the dell'Aquila theory, induces in the cross-section tension in the lower part and compression in the upper part. So we need to use basically a material which is symmetric in tension and compression. Which material is symmetric in tension and compression? Typically steel and timber, of course. So timber is very suitable for use in a beam kind of structure. Of course, concrete or masonry is not suitable because concrete, as you know very well, masonry is very good resistance to compression but very bad in tension. So we can use concrete alone at least. So if you want to use concrete, as you know very well, we need to couple concrete with steel, either a steel beam or a steel reinforcement. Or also, we need to couple concrete with another material, also with timber. So if you think about having a timber concrete composite beam where we place the timber, a timber beam underneath in the tensile region, and we place concrete in the compressed region. Another possibility to cover a certain span is the use of trusses, the travatura reticolare. In this case, the resistance to vertical loads is achieved by basically axial forces, compression, again, and tension. While before compression and tension were the same cross-section, in this case we have some members, some linear members that are subjected to tension, some others are subjected to compression. Again, this solution is suitable for symmetric materials like before, steel and timber. The third option is to use arches. In this case, the resistance to vertical loads is primarily achieved by compression. So, in this case, if you want the shape, is done in such a way that the main forces acting in the structure is the compression force. And this is suitable for material with good compression strength. Again, timber, again steel, and in this case we can also add masonry and concrete alone. Final option, there may be some other option, but let's say the final important option is the use of cables. So cables are materials, structural members, that are only able to resist tension. In this case, again, the resistance is achieved by shaping the structure in this way. If you want, you can see this like an arch turned upside down. While before, in the arch, we had only compression and stress. In this case, in the cable, we have only tensile forces. Now, we said that the basic, the focus of this lecture will be mostly, we said, on arches. So, the basics of an arch structure, as we said before, is that the arch under vertical load shall be subjected mostly to compression. So the arch must have a shape like this, a curved shape. And of course, we already discussed this. In order to make sure that this carved element will be had as an arch, we need to make sure that the restraint will not move. So the two restraints usually are pin connection, they are not fixed connection, pin connection, they are hinges. However, both of them must be hinges, so we can't have a hinge on one side and a roller on the opposite side, because in this case, of course, we would have the compression as the main force over the structure, but we would have bending as the main force over the structure. You can see here, in this sketch here, of course, if you have two rollers and you apply a vertical load, you can't really get the equilibrium. So it's important that the supports are pin connected in order to get a member which is mostly subjected to compression and not to bending. We've already seen this photo here. You remember the remark was that here is a pin, so this is a pin, pin and another pin, it's okay. However, here, to make sure that this pin doesn't move horizontally, we need to connect this restraint, the arch, with a laterally rigid cantilever. In this case, as you can see, the cantilever is made of reinforced concrete to make sure that under this lateral load, the horizontal deflection will be limited. Because the bigger the lateral deflection, the lower the compression, the higher the bending moment. In order to understand better this concept, actually now we're talking about another concept, sorry, we understood that we need to have the pin connection here, and then there's another important effect of the shape of the arch. Now suppose that you need to cover the same span. We said, okay, we need to have a pin connection on both sides. So how does it vary the force, the compression force within the arch, and also the restraint reaction, as we change the geometry of the arch? So on the same span, we increase, or if you want, we decrease the rise of the arch. So we start with an arch characterized by a high rise, and then progressively we reduce the rise. So we change the form, the shape. So how is it going to change the compression force within the arch? So from the equilibrium on the same vertical load, as you can see from the equilibrium, the component, the vertical component of the reaction is the same in all three cases. So there is no difference in terms of vertical component. Could have been different because from the equilibrium, the sum of these two forces must be the same as the result of the vertical load, which is the same in all three cases. So this vertical component is the same. However, as you can see, as we move from this scenario to this scenario here, since we said in an arch, basically, the main force is the compression, we can expect here on this joint that the restraint reaction will equilibrate the compression force. And as you can see, this compression force shall be this compression force, or if you want, this one, plus this, plus, okay, should be the other way around, sorry. The opposite of this force here, plus the opposite of this reaction here, plus this result shall be equal to 0. So basically, from the equilibrium, if this is the arch, from the equilibrium, we have something like this. 1, 2, and 3. Equilibrium. So if we keep this force, this vertical force constant, and we change the shape, if we go on a shape like this one is always the same. But of course, in this case, the restraint reaction shall be something like this. So we will end up having an equilibrium like this. So as we reduce the rise of the arch, we increase, you see, the value of the total reaction, in the sense that the vertical component is always the same, but the horizontal component is getting bigger and bigger. So this is the reason why in an arch, if we want to reduce the actions within the arch, we need to increase the rise. So the higher the rise, the lower the compression force and the restraint reaction. Okay? Remember that the limit case when the rise tends to 0 is what kind of restraint reaction? Suppose that you reduce so much this rise to get to a value which is very close to 0. So the restraint reaction will become which value? If this becomes almost random. No. If this becomes 0, the restraint reaction to equilibrate this vertical load shall be which value? So we do a limit. We just think about this. We increase, we go to this case here. So we go something like this. So basically the restraint reaction tends to be very big. Okay? So remember, in order to make sure that an element behaves as an arch, we need to have a little bit of height, because otherwise it doesn't work. Just remember, as an example, this bridge that was designed in Venice by Renzo Piano. This was a bridge with a very small rise, if you remember. The old bridge had quite a big rise. The new one was very flat, very small rise. And of course, the restraint reactions were very big. In fact, they had to build a significant foundation underneath, like I was told, like a building of 5 stories, just to have underneath the ground to keep this reaction. Because of course, the problem, again, when you have very high thrust, the problem is that if this foundation is not fixed, it's not very well designed, immediately you get a displacement. As you get a displacement, immediately you reduce the compression, increase the bending. So it's very important that this restraint reaction is taken by the foundation. And of course, if you have a foundation here, the only way a foundation can resist a horizontal force like this, the only way is to make this foundation very big. Very big in such a way that this self-weight will in some way make this horizontal component more vertical, because the ground can mostly resist for vertical load, not for horizontal load. Of course, also for horizontal load, we need to put some inclined piles and so on. So remember that this is very important, this drawing here, because we need to find a compromise between the rise. And of course, I mean, theoretically the rise should be the highest value possible, but sometimes for architectural reasons we cannot go very high. So if we go to lower rise, we need to remember that the thrust will be very big. So are we able to build a foundation which can resist this thrust, or a structure which can resist this thrust? If we are, okay, then this one will behave as an arch. If we are not, then it's better to design this as a curved beam. So to have as the most important stress inside the bending moment rather than the axial force. Okay? So we can say that in general the arch is the most economical structural form for the resistance of a uniform vertical load over a large span. If you compare the table that I gave you yesterday for the preliminary design of the different structural systems, you will find that for an arch, the thickness is h, so the thickness h is, if I remember well, the length divided by 55. Well, instead from the other is h over 40, and also l over 30, and so on. So the arch is by far the most economical, if you want, structural shape. Uniformly distributed load induces mostly compression, very little bending. However, the most critical load condition for an arch is not the uniformly distributed one, but is the dissymmetric one. So for an arch, usually the load condition which governs the design is this, the non-symmetric one. Because in the non-symmetric one, we get some bending moment additionally to the axial force. So unbalanced loads. Unbalanced loads, as you know, in which case can we have unbalanced loads? You remember? In your design. So when you design, for example, your project, for which load conditions you can have these unbalanced loads? Snow, sure. So the snow you have to consider the unbalanced. Usually we don't do this, but if we design an arch, the balance is, by the way, the most important one. And not on this note, also you saw recently wind. Okay? Then theoretically also the maintenance. The maintenance is a variable load you should consider also that. But we said the snow usually covers also maintenance, so the snow is more critical than the maintenance. Which shape is chosen? Usually a parabola, or for small spans a circle. Sometimes also this elliptical, because often we have to increase, we have the need that in this region here we can do very little because the height is too low. So sometimes with the elliptical shape is preferred because we can increase the height close to the edges. We already said that we have a very high horizontal reactions. Sometimes we are struggling in order to get this reaction down to the floor, down to the ground. Another problem is that this simple arch here has some problem, architectural problem here, because as we said before, the height is very low. So, of course, from the architectural point of view, this solution is much better, because then we can get some headroom here. On the structural point of view, however, the solution is much worse than the other, because you can see that this point here that should be fixed, now they are no longer fixed, because they are subjected to possible horizontal displacement unless this member here is very stiff. So in this case, we need to make sure that this member, this vertical member, is very stiff. So we need to make it, for example, out of reinforcement, not out of timber, in order to prevent the horizontal deflection. This is also a possibility to extend the arch outside the area that is covered. But of course, in this case, we have some weathering problem with the wood, which is exposed to the rain. And also, we need to have more room available, more area available around the building. This would be, from the structural point of view, a very effective solution. So we could put a tie rod here to connect those 2 points. So if we tie those 2 points together with a rod, of course, when we have a vertical load, this rod, by resisting in tension, will significantly reduce the flexibility and will keep the distance more or less constant. Of course, there are 2 problems here. One problem is that, for example, if you have a sport hole, it's not very nice to have this rod. If you have, for example, here to play something, to have this rod in the headroom here is not so nice. And, of course, this rod encroaches this area. You may not be able to have it. And the second problem is that this rod is in compression when the load, the gravity load is downward. If for some reason, for example due to wind, the gravity load becomes upwards, then this rod will go in compression. If it goes in compression, what is the resistance of the rod? 0. Buckling. Well, we said last time we shouldn't say buckling, even though it's right. There's no buckling. It just doesn't have any compression. Okay. And so, that's a possible problem. This is another solution to use, you see, to realize here, basically, to have a room inside here for the athletes and here for the spectators. Now, in terms of preliminary design, some advice. I mean, these arches are very much used for sports hall, I would say. So some advice on preliminary design: the space between the arches should vary between 3 and 8 meters usually. Purlins, also in this case, of course, we need to use some purlins to sustain the roof area. And the purlins, the best solution with the purlins is those purlins extending over a significant depth of the main arch in order to provide some lateral restraints that are useful then when we do the out-of-plane lateral torsional buckling verification of the arches. There is this ratio that should be in some way complied with. So the ratio between the spacing and the span should vary between 1/4 and 1/6. 1/4 for short span buildings and 1/6 for long span buildings. In terms of bracing, the most economical system is using diagonal steel tension bracing. So what we saw so far. Of course, we can also use diagonal, simple diagonal timber bracing, tension and compression. That is probably the most economical one. This is an example of what we saw before. So a number of arches. You see 3 pin arches, 1, 2, and 3. Some purlins. Those purlins, as you can see, they are very small compared to the height of the arch. So they don't provide enough. Well, in terms of lateral torsional buckling, probably they don't provide very good support. So in this case, we need to refer to this point here, where there is the bracing system. You see, there are some bracing made of steel rods. Where there are the bracing, there is an additional purlin. As you can see here, we have the normal purlins, which are above the arch. And then we have an additional member just underneath here, the normal purlin, to take the axial forces due to the bracing forces. Here we have one bracing, here we have another bracing. Note also that this arch here is a taper kind of arch. So the minimum thickness is here, the minimum depth is here, and then the depth is variable, and you get a higher value there. So usually now you will see that the arch should have the minimum thickness here, reduced thickness here, and the maximum thickness in between to optimize the behavior. So usually, in this case, the material used is always glue laminated, because the only material that we can be formed in order to get the curved shape. Main limitation is transportation. For not very big sports hall, we should reduce the height of the arch to 1.4 meters. The breadth is between 65 to 130 millimeters. And then there is this ratio here. You see that the ratio between the rise and the span should be more or less 1/4. So if you need to cover one span of 100 meters, which is a huge span, the height should be 25 meters. Why should we respect this ratio here? Basically to make sure that the forces here are not too big, that the strength reaction are not too big. Sometimes at the foundation level, there are some solutions where we do a tie connection in reinforced concrete between the different footings in order to keep this horizontal component. So instead, you see before the possibility to put the tie in the headroom inside, and the possibility to put the tie in the foundation directly. The glue gun section are usually tapered, so rastremapped. So you see here what I said before. If we call H the depth of the member more or less at this section here, which is the section where we can expect to have the maximum bending moment due to a balanced loads. The ratio of the depth at the apex of the arch and the depth here should be between 1/2 and 1, and the section of the edge of the arch at the support and the depth of the arch here should be more or less between 3/5 and 1. Also, depth of the arch divided by breadth of the arch should be 2 to 5. So those are just some numbers that are useful when we do the preliminary design of our structure. And here you can see the table, some of the tables that of course were shown yesterday. As I said before, you see for a 3-pin arch, the spacing should be between 5 and 15 meters, for 2-pin arch 5 to 20, span 20 to 60, span of the 2-pin arch 20 to 100, and the depth, you see here, L over 55 and L over 50. If you compare this with the other members, for example, taper and camber beam, you see that the ratio are much lower in this case. Of course, after the choice between 2-pin and 3-pin arch is based on some concept that we saw already said yesterday for the portal frames. 2-pin arch are statically determinate, so any horizontal vertical central support will induce moments in the arch. 3-pin arches are statically determined, so they are more tolerant of flexible support conditions and also of possible differential settlements of the foundation. Of course, a 2-pin arch, the problem with a 3-pin arch should be designed in such a way that the two halves are transported, are prefabricated, transported within the design, and they are connected together. The 2-pin arch, in general, it's not possible to transport the 2-pin arch all together on the building site perfectly. So we need to find some splice joints. For example, splice joints are in this condition here, where the bending moment are not the maximum one. Okay, fully fixed base instead is unusual. And this solution B is a 2-pin arch made of 3 pieces, where the splash joints are located more or less at the third. So it should be the points of zero moment under gravity loading. So, we said before that arches are the most effective systems to resisting uniformly distributed load. However, they are much less efficient. You can say that for uniformly distributed load, they are much more efficient than portal frames. However, for unbalanced load, they are not very efficient. So wind usually results in non-uniformly loading, also snow, particularly when there is a snow. When there is a snow, now we don't go into detail, we already see this regulation, but you can see here, when there is a snow, we have to consider two load conditions, and with the uniformly distributed one, which we know won't be the critical one, but then we have also this other load condition, as some of you mentioned before, with unbalanced load. So this one may dictate the design of the arch. So this unbalanced load condition. For the wind, I don't say anything because we already seen it a lot with Dr. Sciomenda, so you know that wind is it's a kind of problem in the sense that you have many conditions, some of them are unbalanced. Here you have some tables for preliminary design for a 3-pin arch. So you see the load condition, Q on one side and alpha Q on the other, and different curves when alpha changes from 1 to 0.5. Those tables for preliminary design are drawn for this ratio between the rise of the arch divided by the span equal to 0.14. So for this geometry, if you enter in this plot here with Q over S, where S is the spacing of the arches, so Q, uniformly distributed load, over S, over, Q would be the uniformly distributed load, on your arch, divided by S, which is the spacing, so kilonewton per square meter, over FMD, which is the design strength of the Luna. So if you enter this plot here with a number, then depending on the imbalance between the loads, you will find here one curve, so you will find a number, for example 0.020, and this would be the ratio between H, the maximum depth of the arch, and L, which is the span of the arch. So those plots can be useful again for preliminary design. when it comes to sketch the first shape of our structure, of our arch. Then, of course, there is a significant difference from a structural point of view between arches and curved beams. They both might have the same shape, but the structural behavior is completely different. An arch, as we said before, is mostly subjected to axial force compression, while instead a curved beam is mostly subjected to bending moment. So here you see a curved members with a support on this steel column, and then we have a support on the opposite side. Now, do we have a doubt? I mean, the doubt would be, is this an arch or is this a curved beam? Of course, it's a curved member. This curved member may be had as a curved beam or as an arch. How can we decide if this is an arch or a curved beam? This is the easiest way. We look at what? Yes, we look at the support. Is this a pin connection? This one is a pin connection. Why not? It's not a pin connection, this. So if you look, you have something like this, then you have a column. Which connection is here? It's a fixed connection, it's a pin, it's a roller, what kind of connection is here? Problem. So what kind of connection is here between this and this? If you look here, is this connection able to transfer a bending moment? What do you think? Okay, now we can't see the detail, but you can see that there is an arch down in this way. Go down this way, then here there is something like this, and then here there is the column. Now, I don't know exactly here. Something like this. So, is this, what kind of connection is this? First of all, is it an internal connection or external connection in terms of structure? If I model the entire structure, is this an internal restraint or external restraint? Well, when I model this structure in the sub 2000, for example, think about how to model the structure in the sub 2000. How would you do it? So you have a structural member here you have a foundation, then you have another structural member here. So this one, in terms of classification, would you consider as an internal, a connection internal to the structural system or external? This is just a matter of one definition, conventional definition. But so, it's an internal connection. It's a pin connection. What's a pin connection? Well, more or less, think about the bending moment. Is this connection able to transfer a bending moment from here to here? No, because the two members are too different. To be able to transfer a bending moment, this one should be in some way extended. It should reach up to here in order to take here compression and tension that you have on the different upper and lower sides, right? So only this one could be a fixed connection, a rigid connection. But since instead finishes here, there's a internal pin connection. Now, we discovered that this is a structure like this, more or less. And then here we have probably something like this. And then here we have another support, for example. We don't know the support of the opposite side. But the point is, when I apply vertical load here, this one behaves as a curved beam or as an arch. Correct? Yes, why? Why is a curved beam? Yes. So here the bending moment is 0. But also in the arch the bending moment is 0 in the support. Cannot this be the reason why it is not an arch? Because the arch, the bending moment, we said is actually 0 everywhere. So, again, how can we understand if this behaves as an arch or as a curved beam? What do we need to look at? Okay, it's not symmetric, but because we can't see very well. Okay, suppose that this is symmetric. It goes down on exactly the opposite side, right here. Because you can't see that. The type of which kind of connection?
The corner one.
This one. This one is a pin connection. Okay, so the fact that this is a pin connection, also in the arch is a pin connection. But what's the difference? This one, what? In an arch, yes, here there is a bending moment, but here there is a 0 the bending moment. It's not continuous. So, is it an arch or is it a curved beam again? Probably, since the title is curved beam, probably something would say, okay, it's written curved beam, probably this one is an example of curved beam, but we need to understand why is it a curved beam and not an arch. So what are we going to look at? Because again, a curve and an arch beam, they have exactly the same shape. They can have exactly the same shape. But in one case, the curve is an arch, in the other one is a curved beam. So in this case, how can we guess that this is a curved beam and not an arch? To be an arch, what should we have? So, to be an arch, what? We said before, some rules for an arch. You remember? Yes, exactly. All the cross sections have been compressed. Why this one is not compressed, all the cross sections? What we need to look at?
Perché lì ho una forza che esce fuori dal gancio facendo la inerzia con il pilastro.
Yeah, but now we look at the curved beam, not at the column. So the fact that this force is outside the kernel of the column, I don't care. I mean, the column will be subjected to eccentric axial force, to bending. But of course, the column is made from steel, it can resist the bending without any problem. So, we try to, if you remember what we said before, for an arch, what is important? To be an arch, the prerequisite for a curved beam to be an arch, what is it? Yes, transfer compression forces, but in order to achieve this, what do we need to have? Well, the rise over span ratio, okay, but this is curved, it has a rise. So what else? What do we need to check? Yes. But okay, here, how can we know the horizontal forces here will be small? Okay, here the horizontal force, if this is an arch, the horizontal force will be something like this. So this will be the reaction. So there will be those two components. Okay? Now if you look at this structure here, what can you expect? That due to this horizontal component, what's happened there in this connection here? You remember we said the typical static scheme of an arch should be this one. You see here? Is it the same here? So what's the difference between this and this? The
shear force.
in the arch, the shear force in the arch is this one. So an arch to behave as an arch, if we go back, this is the scheme. Of course, this is another possibility. By this possibility, what is going to happen? Which is the possibility here. So, if you look at this static scheme, like we saw before, so the basic is that we need to have steel supports and or reinforced concrete foundation to ensure little lateral displacement. So, in other words, this point here should be fixed, should not move, or should move very little laterally. Because this is going to move laterally, what's going to happen? That the bending moment is going to increase, and the axial force is going to decrease. So the problem why this, I think this system here does not behave as an arch but as a curved beam, is that this support is very flexible in the horizontal direction, because as you can see it's made of steel, very slender steel column, which will be subjected to some horizontal forces. So for sure, here we will have a deflection like this. So as this deflects horizontally, the arch is going to move, and this movement of the support is going to reduce significantly the compression force to increase the bending moment. So in other words, here we are almost sure that this is curved beam because those columns made of steel are very slender, and they are not able to act as a fixed, let's say, as an external pin connection for the beam itself. Okay? Is that okay? Is that clear what you said? Okay, now another important topic concerns taper, curve, and pitch cover beams. So glue laminated beams are often tapered and or carved in order to solve some of the also architectural problems. Here you can see the most commonly used types. So single taper beams, which are the drawings with A, curved beam with constant cross-section, number B. Then we can have double taper beam, number C. Pitch camber beam, this one, number D. Then we have what is called fish-bedded beam, the number E, which is, I wouldn't say, not much used, but it's also another possibility. So the first four are the most used possibilities, I would say. So, if these members are made of Plula, it is recommended always that the lamination should be parallel to the tension edge of the beam, with the taper edges located in the compression edge, which doesn't mean, what does this mean? It means that if you have a beam subjected to mostly to positive bending moment, so the positive bending moment will induce compression in the upper part and tension in the lower part. In this case, the lamination should be done with the member, the glue lamination should be done with the lamination, so the single board, parallel to the tensile side, and the tapering should cut the lamination on the compression side. So, again, For positive bending moment, this is okay. Instead, if we have a beam which we know is subjected to mostly negative bending moment, this solution is wrong, or should be avoided. So in other words, the lamination should be parallel to the tension edge of the beam. So positive bending moment means tension below the compression underneath. Negative means compression below and tension underneath. So the tensile side should never be the taper part, so the one with crossing the lamination themselves. Another important point is that in this kind of beams, in these taper beams, the distribution of bending stresses is nonlinear. So the bending, the M&M theory does not apply anymore in this kind of taper beams. However, for design purposes, the maximum bending stresses at the taper edge can be calculated with some approximation using the simple bending theory and modified by a factor. So also in these beams we will end up using the M&M theory, so the usual formulation, with the introduction of a correction coefficient. This correction coefficient will take into account the fact that the reality in these beams here, the distribution of stresses is no longer linear, but it's not becoming non-linear. In general, we could say that taper, curved, and pitch covered beams and arches have lower strength than straight members due to three things. First of all, bending pre-stress in the lamination. So the fabrication process involves bending some of the planks and then gluing them. This action of bending the planks induces some higher stresses, so some residual stresses. This reduces the strength compared to a normal straight member. Then we have a nonlinear stress variation over the depth. So unlike the M&M theory, in this case we should consider a nonlinear stress distribution. And then we have, in curved members, stresses perpendicular to the grain. So we have a secondary stress perpendicular to the grain, which is superimposed to the main primary stresses parallel to the grain, and reduces, of course, the strength of the member. So let's start with analyzing the first problem, which is bending pre-stress in the laminations. So, during manufacture, the individual laminates, so the single planks, are bent to the desired form before the glue has hardened. So first we bend the planks, and then we leave these bent planks with the glue, we leave them for a certain period to ensure that the gluing goes off. So which means that as we bend the planks and we glue these planks together, we induce some additional stress in the structure. Also, because if you have a plank, you bend, you need to force, you need to apply a force. So you stress the plank themselves. Then you glue it, it means that you incorporate some, we call eigenstresses, so autotensioni, in your structure. So your curved glulam structure, when it is formed, has some significant eigenstresses inside. Okay? Then what's happened, as time goes by, timber creeps. You know, the timber has some creep behavior. And so we have what we call relaxation. So those stresses, as time goes by, reduce over time due to relaxation and creep. So after 1 month, if you measure the stresses immediately after you bend the lamination, you will find, for example, a certain number 10 megapascal. Then if you come back after 1 month, you will find instead of 10, 5. If you come back after 1 year, you will find 3 or 4. This is due to the relaxation, the creep of timber. So in the end, after the long term, you will have that the initial eigenstresses stresses will be reduced very much. However, we have to take them into account, particularly when we use some radius of curvature. So when we bend those laminations to some small radius of curvature. Obviously, the lower the radius of curvature, the higher the stresses. There are some limits, so we can't really, with a normal 40 millimeter thickness board, you can't go on a radius of curvature of say 3 meters, because you would probably break the board itself. So you have some limitation. However, if you check if the radius of curvature is quite small, you may have some significant eigenstresses anyway. So this means that the effect on bending strength of small bending radii must be taken into account. And this can be done by multiplying the basic value of bending strength by a reduction factor, Kr. So already yesterday we saw that it was F and D multiplied by Kr. This Kr is the reduction factor taking into account these eigenstresses due to the curvature induced on the board. So if you take, for example, this clause from the Euro 5, it is written that in the apex zone, the bending stresses should satisfy the following expression: sigma ND less than or equal to FMD times Kr, where Kr takes into account the strength reduction due to the bending of the laminates during production. So in other words, we reduce the strength, the design strength, to take into account the production process which induces some eigenstresses, additional stresses in the structure due to the bending process of the blank themselves. And we take into account this by multiplying the design bending strength by Kr, strength reduction coefficient. Kr assumes different value depending on the different case. For example, for a double taper beam, Kr is equal to 1. So it's not important. For carved, so you see here an example of carved beam, and underneath an example of pitched cover beams. In this case, Kr may be equal to 1 for Rin over T greater than 240. Instead, is equal to 0.76 plus 0.01 In divided by T for this ratio less than 240. So, as you can see, the value of Kr is linked to the ratio between the radius of the arch, the minimum value of the radius of the arch, and the thickness of the lamination. Of course, the higher the thickness, the higher the stress. So everything depends on this ratio between R, the inner radius of the lamination, and the thickness of the lamination. If this ratio is greater than 240, we can ignore those eigenstresses. If this ratio is lower than 240, we need to take into account this eigenstresses by considering this reduction coefficient. Now, if you look at this ER386, that is about new laminated timber membrane, we will also find that the maximum permitted laminate thickness in current structural components is given by this relationship, which means, as I mentioned before, that there is a limit. We can't really bend a board to a radius which is too small. You see here, for example, that for GL32 and 40 millimeter thick lamination, so for a board which is 40 millimeter thick, which is the most common one, the minimum radius is 7 meters. So we can go below 7 meters. Okay? And anyway, after we need to check, when we do the verification, if we need to reduce with the Kr coefficient the strength, the design bending strength or not. You see here that Kr is less than 1 for this inner this radius of inner lamination less than 240 times t, which means 9.6 to 10.8 meter. So in other words, we can't bend this lamination on a radius less than 7 meters. From 7 to, let's say, 10 meters, we need to consider this reduction coefficient. For radius greater than 10 meters, we can ignore this KR, because this KR becomes equal to 1. Okay? Okay, the second phenomenon that we need to take into account in curved beams is the nonlinear stress variation over the depth. So when we move from straight members to curved members, we find that there is a significant difference in the stress distribution. While for straight members, according to the Descevenant problem, Descevenant theory, there is a linear variation of strain and a linear variation of stresses. In curved members, we have to consider, and we should consider, a non-linear variation of stresses over the depth when the curved member is subjected to bending. So, consider now a small piece of a curved member, like here, subjected to, for example, sagging bending moment, so positive bending moment. Suppose that the neutral axis is at mid-depth, like in the case of the Descevenant theory. So suppose that the neutral axis is at mid-depth here. So you would find then that we have some compression in the upper fiber and tension in the lower fiber. So if the distribution was linear, like in the Descevenant theory, with neutral axis at mid-depth, we would have that. Let's put it this way. Suppose that the distribution of the epsilon, so we still have this principle of conservation of the plane section. So suppose that the cross section is initially plane will rotate around the neutral axis, which is assumed to be a mid-span. So initially, this is the cross section, and then this cross section rotates around the neutral axis. So we would then get a strength here. Well, we will have a stretching here. Well, sorry, a squashing here, and a stretching in the lower part. Even if we assume that those two values, delta L0, so this compression strain on the upper side is the same as the tensile strain on the lower side, even if we assume that those two values are the same, when we calculate the epsilon, which is the strain, of course we need to refer to different initial length, because in the upper part, the length of the fiber is L0. In the lower part, the length of the fiber is Li. Why is that? Because it's a curved beam. It's not a prismatic beam. Meaning that we have the same delta L, but the denominator, which is the initial length, is different above and below. So we would have the delta Li over Li in the, let's say, the lower fiber would be greater than delta L0 over L0. Even assuming that delta Li and delta L0 are the same, because Li is less than L0. So this shows that in terms of epsilon strain, the strain in the lower fiber, epsilon I, is greater than the strain in the upper fiber. If the material is elastic, this means that the stress in the lower fiber, sigma I, will be greater than the stress in the top fiber, sigma O. Okay? So if the stress are different, it means that the neutral axis can no longer be bicentric. Of course, if those are different, if you take a line, you will find out that this line will cross the vertical line, not in the not at mean height, but at a different depth. So in other words, if we repeat again, if we assume that on a curved member the principle of conservation of the plane section still holds, so we have this initial cross-section which is plane which rotates around the neutral axis, we would end up with having the same deformation, well, the same, I would say, squashing on the top fiber and stretching on the lower fiber, so delta 0, delta I would be the same, but the initial length of the fiber is different, because del I is less than L0. So this means that epsilon I is greater than epsilon 0, and this means also that for an elastic material, sigma I is greater than sigma 0. If there is this difference, the neutral axis can clearly not be anymore at mean height. But as you can see here, for the equilibrium, the neutral axis should be a little bit on the lower side, should be lower level. So this determines in the end that this distribution is no longer linear. So we can say that the distribution of sigma is no longer linear, it's non-linear, because so is the distribution of strength, even though we started from a linear distribution of this value delta n. So we started from the principle of the conservation of the plane section, which is the basic of the Navier formula. But in a prismatic beam, this means that also the epsilon linear, also the sigma linear. In a curved beam, this means that the epsilon not linear, and also the sigma becomes non-linear. In particular, in this case, we will find out that the stresses are hyperbolically distributed along the length. So we have a distribution like this. So, for design purposes, the regulation considers always the validity of the Tesla formula, the bending formula, but introduces a correction coefficient. So in this case, we can calculate sigma md using the normal Navier formula. So 6 times MAPD divided by PH square AP is the Navier formula basically, because it's M over BH squared divided by 6, so M over the section modulus. But in this case, as you can see, we need to multiply this decimal formula by a correction coefficient, which is called KL. This correction coefficient is given by this relationship that we can find here. So we have some kind of approximate relationship. So KL is it depends on the 4 coefficients K1, K2, K3, and K4. K1, K2, K3, K4, as you can see here, depends on tangent of alpha AP. So alpha AP, you want to see alpha AP is the inclination of this line with respect to the horizontal one. So alpha AP, or if you want, in the case of a taper beam, is the inclination of the tapering. So it would be basically this. So the correction coefficient, KL, depends on alpha AP, so the inclination of this tapering, and depends also on this ratio between HAP and R. HAP is this. So in this case, in the case of a pitch camber beam, HAP will be this value here, and R is the radius of the middle fiber. So R is RIN plus 0.5 HAP. So in other words, if we go back to the formula, we have a general formulation where this reduction coefficient, or this modification coefficient, it's not a reduction, sorry, it's a modification coefficient that we need to put within the Navier formula, depends on the inclination of the tapering, and depends also on the ratio between the depth of the cross-section of the apex and the radius of the laminations. The radius of the lamination, you can see, is the inner radius. So, for example, in this case, this is HAP, this is alpha AP, this is RIN, and R is this value here. R is this value in the middle here. So R equals the inner radius plus HAP divided by 2. MAPD is the design bending moment in the apex. So MAP will be here. So, if we plot those functions there, so we said before, we have a KL. So KL is a function of this ratio HAP over R. It's also a function of alpha AP. So, if we consider, for example, just a curved beam, in a curved beam, we have that in the curved beam we have that this angle alpha AP in the curved beam, since this is not tapered, alpha AP is equal to 0. So the corresponding function is, corresponding curve is given by this red curve here. So as you can see, we have a coefficient in general greater than 1, so if we have that the radius, the ratio HAP over R tends to 0, which means that the beam is not curved but is straight, obviously this coefficient must be equal to 1. So KL must be equal to 1 because in this case the maximum stress is given by the Nonlinear formula. So in other words, what we are doing now with this formula, we are going to increase the maximum stress, which is, if you remember well before, is the lower stress. So you see, if you consider, if we were to use only the Navier equation in this problem, you would find that the sigma O would be slightly greater using Navier, and the sigma I would be slightly, the actual, the value of the sigma I using the Navier equation would be smaller. So the actual sigma I is higher than the value that we calculate with Navier. So we need to introduce an increase in a factor, a coefficient higher than 1. This coefficient is called KL. So when we calculate the maximum tensile stress with Navier, we need then to multiply this value by KL. For a curved beam, KL is given by this red curve. So basically it would be KL would be given by K1 only because HAP over, let's see, K1 would be given by K1, so K1 would be 1, so should be KL is 1 plus K2 would be 0.35 times HAP divided by R plus 0.6 plus 0.6 times HAP over R divided by 2. So it's basically this curve here. So if HAP over R is equal to 0, which means that the curve beam is actually straight, of course, the Navier equation is the right one. So we would find that KL is equal to 1. As HAP over R increases, so as we have a more curved beam, then we can get up to a coefficient, as you can see, up to more or less 1.2 for HAP over R equal to 0.3. If you have instead a pitch camber beam, then in this case we have a family of different curves that depends on the value of this angle of the tapering. So from 0 to 25 degree. In this case, as you can see, that this value of KL can raise up to even 3. So we have to even to multiply by 3 the bending stress we calculate with the formula of Navier. Last case, if we have a double taper beam, in this case, we have to move along this green curve here, because in this case, we have that HAP over R is equal to 0, because we have no curvature of denomination. And so, as this angle of cutting, this cutting angle of the taper increases, this coefficient moves from 1 up to almost 2.8. So definitely not negligible. So again, when we have to deal with this kind of beams, we have to remember that we can use the Navier equation, but then we need to multiply the stress we obtain by this KL coefficient that we find using this equation. Okay, the third phenomenon that we need to take into account is the possibility to have stresses perpendicular to the grain in curved members subject to bending. So suppose now that you have one piece of a curved member like this, and suppose that this piece of curved member is subjected to positive bending moments or optic bending moment. Okay? For simplicity, for the sake of simplicity, assume that you have a linear distribution of stresses, even though we learned before that the distribution of stress won't be linear, will be non-linear. But not just for the sake of simplicity, because it's not going to change significantly the problem. Just suppose that we have a linear distribution of stresses. So, suppose that this piece of beam is very small, so we have a very small angle, the theta. The radius of the axis of the curved beam would be RIN, so the inner radius, plus 0.5 times h, where h is the depth of the section. We call dl the length of this piece of geometrical axis in the mid-height or mid-depth of the beam. Of course, dl will be given by RIN plus 0.5h multiplied by d theta. So, geometrical relationship is this one. Now, if you study the equilibrium of this small piece of beam, which are the forces that act on this small piece of curved beam? Suppose we have no external loads here, so we have only this equilibrium between the compression force and the tension force on one side, and the compression force and the tension force on the other side, where those compression force and tensile force comes from this distribution due to the bending moment. So the bending moment induces a compression force in the upper part of the section, a tensile force in the lower part, and the same occurs on the opposite side. Now, when the beam is straight, those two forces, so if you have a piece of beam which is straight, like this, So if we study this equilibrium here, of course we will have a compression force here, FC, FT, and FC and FT. Now those forces are the same, so basically they just compensate one to the other. However, if the beam is not straight but is curved, if we study now the equilibrium of this piece of beam, the situation, as you can see, is different from this case here. It's quite different, I would say. Because in this case, of course, when I do the equilibrium, of course, the system is in equilibrium, but as you can see here, I do the equilibrium of this force here. And I get one resultant here. And one resultant here. Those two resultants are clearly making or subjecting this piece of beam to tension. So this tension is actually tension perpendicular to the plane. So it's a very dangerous case of stress distribution for the beam. Obviously, if rather than having a bending moment, positive bending moment like this, we would have a negative bending moment. The negative bending moment, what would be the difference? If we have the same value of moment, but not positive, but negative. So in the end, we will have what kind of stress within the beam? Which means?
This direction would be...
Yes. So in the end, would be now we have a tension perpendicular to the brain, the other case would be compression perpendicular to the brain. And obviously, if you have a positive bending moment, but on a beam like this, this would be again compression. So in the end, if you want, if the bending moment that acts on your curved beam tends to increase, so if due to the bending moment tends to straighten the curved beam, to increase the radius, then we are sure that we will have some tension perpendicular to the ground. If instead the bending moment tends to curve further, to bend further the curved beam, then we have compression perpendicular to the ground. Both cases are not very nice because we have stress perpendicular to the brain, but by far the worst case is the one with tension perpendicular to the brain. So we need to be very careful when we have this scenario, tension perpendicular to the brain, which means bending moment tending to increase the radius of the arch, of the curved beam. In this case, we need to be very careful because we have, of course, tension perpendicular to the brain. So if we go back to the initial case, we said that those two forces, FC and FC, will reduce one force, du, tension perpendicular to the brain. So this force, du and du, will reduce some stresses on this middle fiber. So this, if we calculate this stress will be sigma T90, so tensile stress perpendicular to the brain. This will be the actual force, the tensile force du, divided by the section. The section on which this force acts is dl, so the length of the middle fiber, dl, times b, the breadth of the cross-section. Now, from this geometry of the problem, we can find out that du is, so if you multiply fc, so fc times would be times sin of d theta divided by 2, times 2 would be du. So du here is equal to fc times half of this angle, so will be times the sin of half of this angle, so we will have to write that du is equal to fc times sin of d theta divided by 2 times 2. Okay? Now, since the angle is very small, sin of d theta divided by 2 is mostly equal, basically equal to d theta divided by 2. So the sin can be confused with the angle itself, because the angle is very small. And so we get this expression here. If you replace this expression within the one before, and if we now remember that fc and ft can be calculated using Navier formula, so it's basically 1/4 of sigma n, so where sigma n is the maximum bending stress. So sigma n times 1/4 of dh, because of course this triangle here, the area of this triangle is sigma n times h divided by 2. So fc, if you look here, fc, if this is sigma n, fc will be sigma n times b times, this is h, times h divided by 2 and divided by 2 because it's a triangle. So you get this expression here. Fc is 1/4 sigma n times b times h. So if we replace now in this expression here max, sigma T90 is du, we say is fc d theta, divided by b dl, b times dl, so r plus 0.5h times d theta, and then we can replace fc with this expression here, 1/4 sigma n times b times h. We can simplify the theta, we can simplify here b with b. So in the end we find that max sigma T90, so the maximum tensile stress perpendicular to the brain, is given by sigma n, which is the bending, let's say the normal Navier bending stress parallel to the brain, times the coefficient Kp, where Kp is given by 1/4, so 0.25, times h divided by r in plus 0.5h. Okay? So we found this approximate relationship to calculate the value of the tensile stress perpendicular to the brain at curve P. So if you look at the Eurocode provides a formula to calculate this greatest tensile stress perpendicular to the brain to the bending moment. So again, sigma T90D, which is the design tensile stress perpendicular to the brain, can be calculated using the using the Navier equation and multiply the sigma you calculated with the Navier equation by the coefficient Kp. So Kp, as you can see, is given depending on the ratio again between HAP and R, and depending on the tangent of the inclination of the angle of the tapering. Particularly, you can see that Kp is equal to 0.25 in the case of a curve B. So what we found before is 0.25. So 0.25 times H divided by R in plus 0.5H is basically this relationship here. 0.25. So as in this case we have a number of curves. So if you have a curve B, the relationship is Kr is equal to 0.25 times HAP over R. It's the relationship that we found before, that we derived before. So if this red curve, which is basically a line, it's a linear relationship between the tensile stress perpendicular to the grain and the ratio HAP over R. If we have a pitch camber beam, we have a family of different curves. You can see that we can have value up to 0.14. This is 0.14 of the main stress. So basically, the tensile stress perpendicular to the grain can grow up to 14% of the main bending stress parallel to the grain, which is a lot, because I remind you that the tension perpendicular to the grain, the resistance of finger, is value, we're talking about 0.5 megapascal. When you said parallel to the grain, you can get up to 20 to 30 megapascal, completely different behavior. It was very dangerous. And for double taper beam, again, we move along this line here. So we can grow from 0 to 0.10. So another relationship for the Eurocode for the ultimate limit of tension perpendicular to the grain, the apex zone. So we saw that we will have this kind of beams, so curved beam, pitch camber beams, and taper beam, double taper beam, we will have some tension perpendicular to the grain. So we need to check the beam of tension perpendicular to the grain using this relationship in the apex zone. So sigma T 90D, which is what we calculated with this relationship, Kp times 6m divided by P over H squared, shall be less than or equal to Ft90T, which is the design tensile strength perpendicular to the grain, times K volume, which is given by this relationship here, times K dis. Takes into account the effect of the stress distribution in the apex zone, and is equal to 1.4 for double taper curved beams and 1.7 for pitch camber beam. So V0 is the reference value 0.01 cubic meter, and this is the stress value of the apex zone in cubic meter. It's basically the regulation tells you what to consider. So, of course, it also forms a bit more if you want, just to know that there are taking into account about this phenomena. The most important thing, if you want, is this concept which is shown here. So, if you have a curved member subject to positive bending moment, you can expect to have some possible cracks due to tensile stresses perpendicular to the grain. In the case of camber beam, in the case of concave beam, which however not used, then you would have compression perpendicular to the grain. So the first case is by far the most important one. And usually, in this kind of beam, if you have to do this verification, this one, usually this one is not satisfied. If you do your design, you come to this verification, doesn't match. You cannot. So what you have to do it, the only way to make this kind of structure is then to reinforce the structure by using, for example, some plywood panels glued on the sides. We are going to have a lecture just about reinforcement, or by using here some screws perpendicular to the grain, or some epoxy rods perpendicular to the grain to take those tensile stresses induced by the bending moment. So we will have to reinforce the beam. So, in terms of, in general, in terms of taper beam, it's very important to realize that in this kind of beams, double taper beams or single taper beams, the stress distribution is quite different from prismatic beams, the one that we know better from, of course, mechanics of material. So, as you can see, first of all, when we go to check the stresses, we're expecting that, of course, the maximum bending moment demand is in the middle span, mid-span. This is true. The maximum bending moment demand is at mid-span here. However, at mid-span also we have the maximum length. So this means that not necessarily is the highest stress at mid-span, because also we have a variation of the height. In general, I would say, in general, probably the maximum bending stress is not at mid-span. It's in another cross-section, because the height, the depth varies. For example, in this case, you can see the maximum bending stress is in a section like this. Also here, it's not at this value, it's in a different section. Second thing to consider, we have a non-linear bending stress distribution. This non-linearity may be neglected for alpha less than 10 degrees, but in general, as you can see here, we don't have anymore this linear distribution that we have in mechanics of structure, but we have a non-linear stress distribution. The neutral axis is no longer at mid-depth as a consequence of this. So the neutral axis is closer to the tensile side. In terms of shear stresses, we have a non-parabolic shear stress distribution, again as a consequence of the fact that the neutral axis is not at mid-span. So again, Jurasky equation will lead to different, in this case, relationship. We don't have any more the results of the Jurasky formulation. You can see here, for example, the trend of the tau, it's a parabolic. Well, it's a parabolic but with different. Sorry, it's non-parabolic with a different shape. And, as we said before, we have some stresses perpendicular to the grain at the taper edges. So, we have stresses perpendicular to the grain in all this region here, at the taper edge. We're going to see this later. And tensile stresses perpendicular to the grain at the apex, as said before. So, as you can see, the behavior is quite different in this case compared to the one that we know quite well from prismatic beam. So, in particular, perhaps we can close with this, because now it's a longer derivation formula. Where can we find the maximum bending stresses in a non-prismatic beam, a taper beam? The problem is that both bending moment and beam depth vary along the beam. So the maximum bending stress will be at the location x, so x is unknown, the location x where the derivative, the first derivative of the sigma will be equal to 0. So the first derivative of the sigma along the length will be equal to 0. So what we need to do, we can use the relationship that we have in structural mechanics, so m over w. So bending moment at a certain abscissa x divided by the section modulus of the cross section. So the first derivative of this must be equal to 0. Now, since both bending moment and since the bending moment varies with the quadratic distribution along the beam, but also the section modulus varies along the beam, because we said that the depth is different, we need to use this rule of derivation, where the first derivative of a ratio, of the quotient, is the first derivative of the numerator times the denominator minus the numerator times the first derivative of the denominator, all divided by the denominator squared. This is a well-known rule that we study in math. So for a uniformly distributed load, the bending moment at a certain section X would be QL over 2, which is the restraint reaction, times X, minus QX squared divided by 2. For a single taper beam, so for a single taper beam, if this is X, this is HS, this is HAP. On this one, H at X will be HS plus HAP minus HS divided by L times HS plus HAP minus HS divided by L times X. Okay? So this is a relationship from single taper beam of HX. And then we can write the section modulo of the rectangular cross section. So V times this relationship here squared divided by 6. And then of course we need to replace this member here with this relationship here. So the first derivative of the bending moment would be QL over 2 minus 2 times QX over 2. So QL over 2 minus QX times W is this function here, minus N is this function here, times the first derivative of W. So the first derivative of this would be P over 6 times 2 times this times HAP minus HS over L, and here is basically W squared. So this relationship here. Now we can make some simplification, some members can be simplified. So here again we can make some more simplification, because of course we need to find where this function is equal to 0. This function is equal to 0 where the numerator will be equal to 0. The numerator is this. We can simplify number 2, and then by making some calculation, by making some products, in the end we simplify other members and we find this relationship here. This relationship here again is equal to 0 when? Is equal to 0 when, again, X here is given by L in the end. X is equal to L over HS plus HAP divided by HS. So, the maximum of the sigma will be the cross section given by L over 1 plus HP divided by HS, which is in general not half of the cross section, not half of the length. Okay? Of course, if HAP is equal to HS, if we have a prismatic beam, then it's L over 1 plus 1, L over 2. So if it's a prismatic beam, of course it's halfway, half span. But if it's not prismatic beam, it would be in a different place. In general, since HAP is greater than HS, this would be greater than 1, so this would be L over 2 point something. So this means that it will be closer to the left support. So it's closer to the support when you have the minimum depth. So it's not at this span, but somewhere in this region here, okay, depending on this ratio. So this is important because when you are going to do your design, you will be using very likely, because this is very much used, taper member. And with the taper member, you have to find out where is actually the cross section with the maximum M&MoCS. It's not necessarily an expand. So to do so, the best thing to do is what we found here is rigorous only for uniformly distributed load. So the best thing is to ask sub 2000 to ask sub 2000 bending moment different cross section, and then to do the check in different cross section, because we don't know a priori which one is the most stressed one. For a double taper beam, then you can do again the same exercise for a double taper beam. Of course, for a double taper beam, Hx is Hs plus is slightly different than before, because in a double taper beam, we have to put here not L but L over 2. If we do again all the derivation, now you can do on your own if you want, but you find in the presentation. In this case, we find X is Hs over Hap times L divided by 2. This is for a double taper beam, so for a beam done from this way. In this case, this is L, and then you can find where is the maximum bending moment. Okay? Okay, well, for the shear stress, I think we can do next time. So, do you have any question about what we saw today? You can just perhaps say this. On the shears, there is very little you can say because we would have to use a completely different theory. So for this shear stress, there is a stress distribution completely different from the beam theory. We have a nearly parabolic distribution of the support for a small taper edge, and in the end, the only way to find the right distribution of the shear is to use a finite element model. So this is going to be a bit more complex. Okay, so if you don't have any questions, then of course next time will be on Monday. Monday again we will have Dr. Shometa first. I don't know if she will start at perhaps at 2 o'clock, and then we finish with her at 5, because the idea was to do a bit of theory with her, and to continue with the project, which is the most important thing. But 3 hours only the project would have been a bit too much. So perhaps half and half, and then from 5 to 7 we continue on this topic here. Okay.